Is
Hey Mike, you missed it, but this Parker.
okay. Strong bases are bases that will ionize 100%. Okay, they are a group 1 and 2 metals. So if any group 1 and 2 metals are joined with a hydroxide, they're going to be strong, except for beryllium and magnesium right there. Okay. A weak base is one that does not ionize 100%. So they would make a weak electrolyte, and there's some listed there like ammonia, sodium bicarbonate, which is baking soda, and then NaCl, sodium cyanide, which is a poison. I'm sure you've heard of sodium cyanide. Strong acids will also ionize completely. There are your list of 7 strong acids. You should have known that for the last test. Hopefully you did. You still need to know them. And then, of course, your weak acids are one that only ionize slightly. Things like acetic acid, which is in vinegar, vitamin C, carbonic acid, citric acid, and tannic acid, and that's what's in tea.
We were talking about tea earlier.
Iced tea. You can just use... Okay. All right, there are 2 types of acids when we're talking about the naming. So you have to remember how to name our acids. If it's hydrogen and one other thing, we call that a binary acid. And that was hydrogen and one other element. There's no oxygen present, and that's where we use that stem of hydro. So, for instance, if we had HCl, that would be hydrochloric acid. And hopefully y'all still remember that. Okay? If it's an oxyacid, also this is a review, that contains hydrogen with one of the polyatomic ions, which has oxygen in it. And that's where we did the 8 to ick and ite to us. So if we had H2SO4, that's coming from sulfate. So we would call that sulfuric acid. Again, this is just a review from earlier. Yes?
In our notes, it says containing hydrogen with a polyatomic ion.
Oxygen.
Got it.
Yeah, that blank's supposed to be oxygen. I meant to change it before I printed it out. But yeah, polyatomic ion as a polyatomic ion containing oxygen is when you don't use hydro. And then if you had H2SO3, that's coming from sulfite, so it would be sulfurous acid.
Because it was jealous.
It's jealous because it doesn't have as much oxygen. That's right. You were listening.
Yeah.
And of course, when you're naming your bases, that's just like normal naming of ionic compounds because they're going to be hydroxides. So you would have, potassium hydroxide for KOH. If it's with a transition metal, you still have to include that Roman numeral. So if I was doing copper 2 hydroxide, I'd have to do copper Roman numeral 2 hydroxide. So if it's that still stands.
Oh, that was a question. In our lab, how did we know which iron it was? Because I just did iron.
It said it.
It did.
Mm-hmm. I think it said iron 2 sulfate.
Yeah, okay.
Mm-hmm. But when you put the iron in there to begin with, it was just metal.
Yeah.
Yeah. Yeah. Iron 2 is the more common, and so, but I mean, I thought it said it, but.
Just because on number 1 it just said iron paperclip.
Well, iron from the paperclip is just Fe because it doesn't have a charge. It's metal.
Doesn't have a charge.
Yeah, when a metal by itself doesn't have a charge.
Well,
all right, here are some properties of acids and bases put together in a nice little concise thing for you. Things that you probably learned back in junior high. Both acids and bases are corrosive, meaning they're damaging to your tissue. Acids will, of course, eat away certain metals. Acids taste sour. So how many of you like Sour Patch Kids? That's what's making it sour is citric acid on the outside of it.
Is that why your tongue starts bleeding?
Yes, actually, that was going to be my next point. If you eat a lot of them, your mouth starts burning, and that's from the acid in it. Same thing with Skittles. I mean, Skittles, if you eat too many Skittles, they start hurting. Anything that's got that sour, it's coming from citric acid. And that's why it burns after a while. Yeah.
What about
If it's a lab question, can we save that till we're done with nuts?
what about Airhead Extremes?
Anything that's sour is usually, because it's consumer grade and it's got to be food grade, it's going to usually be citric acid. Yeah. Yeah. Warheads, yeah.
Warheads?
Yeah. Okay, so if you remember from when we did single replacement reactions and we had the list of the activity series, acids will react with metals to form hydrogen. When we're talking about phenolphthalein, it stays clear. And of course, if they're strong, acids are a strong electrolyte, and if they're weak, they're weak. And then as far as bases taste bitter. Anybody, when you were a little kid, for saying a bad word, did you ever get your mouth washed out with soap?
I didn't say bad words.
I never had
Okay,
soap
then y'all were all
in my
good
mouth.
children. And maybe by the time y'all were children, they decided that wasn't nice. But when my generation, they would do that. Soap is a base; it tastes bitter. They react with oils they mix. That's what's in soaps, and they feel very slippery or slimy. They'll turn litmus paper blue. They turn phenolphthalein pink, and they also are electrolytes. So those are just some of the characteristics and properties of acids and bases. Now we're getting to the bulk of today, which is what your homework is over is, and the homework is due tomorrow.
Wow.
Yeah. And that is the theories about acids and bases. Okay? The first definition is called an Arrhenius acid and base. Okay? And it is the strictest definition, meaning there's going to be less things under this definition that would be considered to be acids or bases. It's the strictest definition. Okay? An Arrhenius acid is defined as something that will produce a hydrogen or hydronium. Same thing, that can be used interchangeably when it reacts. So it has to produce a hydrogen to be considered an Arrhenius acid. An Arrhenius base,
What's that H3O?
H3O plus. Our Arrhenius base has to produce a hydroxide. Okay? So I gave you one example of an Arrhenius base. An Arrhenius acid would look like this. HCl, when it breaks apart, would form H plus Cl minus. And these are all, of course, in the presence of water. Okay? So it is the strictest definition. Meaning there will be less things that would be classified an acid or a base under this definition. Okay? There's 3 definitions of what acid bases are, and it just depends on who's talking about them. The one that we're going to talk about next is the one we use the most often, and it's most people, when they mean acid bases, is what they're talking about. And it's called the Bronsted-Lowry. Whoops.
Miss Lowry.
Not Miss Lowry. I wish she would, because she'd be famous, but no. Oh my goodness. I'm having some issues today. It's Monday. I left my phone at the gym this morning. I had to run back and get it. It's just
What gym you go to?
20 Anytime Fitness.
Anytime by sign?
I saw your sister there, didn't I? Didn't I see? When I was signing up. Mm-hmm. Okay.
Sister like 9? She's like 14.
Okay, a Bronsted-Lowry acid is one that donates a proton in water. So it's going to donate a proton. Okay?
Do you like the facilities at any time?
Okay, can we do this after the lecture?
Yeah, sure.
Thank you. Bronsted-Lowry base accepts a proton. So whereas the Arrhenius said it had to donate a hydroxide, in this definition, anything that accepts the proton is the base. Okay? And then we have something in this definition called conjugate acid-base pairs. That's supposed to be... that doesn't look like the word acid, does it?
It's like played.
There.
That wasn't better.
Okay, so acid-base pairs are a pair of compounds that differ by the presence of one hydrogen unit. Okay, so the acid will always have one more hydrogen than the base. Okay, and it's basically whatever's left over. So the acid, its conjugate base, is what's left over after it donates its hydrogen. Okay, and so let's look at some examples. Okay, so the conjugate base is this first one. is the remainder of the acid after it produced after it donated its hydrogen. So we started out with the HNO3, it gave away its hydrogen, and so now the conjugate base is the NO3. Okay? Same thing when you do conjugate acid. It's what's left over after the base accepts its hydrogen. So in this case, the NH3 is a base. It accepted a hydrogen, and so then on this side it's the conjugate acid. So it's what goes together. And of course, these are in a reaction together here in a second because you can't have one without the other. So if you have acid-base going on, you can't have just an acid reacting. You've got to have an acid and a base reacting with each other. Okay. So let's look at this first example. HF is your acid, and it is giving away its hydrogen. And so what's left after it gives away its hydrogen is the fluorine ion. So that would be its conjugate base. The water is accepting a hydrogen, so it's going to act as a base. So on the other side, what's left after it accepts that hydrogen is that H3O plus, which is the conjugate acid. And Pat has a question.
Why would that be the base if it says that the base accepts a proton?
It did. It accepted the hydrogen. It went from H2O to H3O plus.
No, the HF and then it goes to F.
Oh, that's a conjugate base. That's different. The base, okay, so that's a good question. He wanted to know why this is a conjugate base?
Mm-hmm.
Okay, so it's the conjugate base because it's what's left over after the acid gave away its hydrogen. They're a pair. Okay, so if I wanted to reverse that reaction, that fluorine would accept a hydrogen and it could be then a base if I'm going reverse. Because remember, many reactions are reversible.
Okay.
Okay, and see that double-headed arrow means that it is reversible.
Oh.
Okay, so let's do these together down here. HCl, is that going to be the acid or the base? Acid. Well, if HCl is the acid, then we know that water has to be the base. What is left over from HCl after it gave away? The Cl. So that's going to be the conjugate base, which is why we're labeling them CB and Ca, because they're a little bit different. So if water's the base, it accepted. That means the H3O plus is the conjugate acid. Okay? It's conjugate acid. So it's left what after water accepted the hydrogen. And the next one, H2SO4 is the acid. And what is left over?
HSO4, which is the conjugate base.
That would be the conjugate base. So again, water is going to be our base. Nope.
Can water be an acid?
Yes, it can.
What?
Look at the next one. NH3 did what? NH3 went from NH3 to NH4.
So it accepted one, so that's the base.
So it accepted one, so it's the base.
Water's the acid. OH is your...
And CH4 is its conjugate acid. I mean NH4 plus. So that means this time water, if you look at it, it's going from H2O to hydroxide. It's donating a hydrogen. So it's going to act as the acid.
So...
And this is going to be the conjugate
Does
base.
that mean water
I'm going to get water.
is sour and is corrosive?
No. Now, there's strong acids and strong bases, okay? Water is special. Remember that. Here's one thing I want you to notice,
Can water be
though.
an acid and a base?
It can.
Is that like the special part about it?
When you have a H3O plus on the product side, it's always going to be your conjugate acid. Okay? If you have hydroxide on the product side, it is always going to be your conjugate base. So that's something to make note of. Okay? Anytime you have these are on the product side, okay? Product side. When you have H3O plus on the product side, it's going to always end up being your conjugate acid. Okay? And then when you have hydroxide on the product side, it's going to always end up being your conjugate base. It's just the way it works out. Okay? So, you already noticed that water, can act as an acid or a base. Okay? That is called something that's called amphoteric. I will spell that for you. I will actually look up, I forgot how to spell it.
Oh.
There's two words that mean the same thing, and I sometimes combine the two words.
It's the cowboy killers.
Amphophthiric. Here we go. Okay? And it is a substance that can act as an acid or a base. And what determines whether it's acting as an acid or a base is what it's reacting with. Okay? So if water is reacting with something that is a stronger acid than it can be, then water will act as the base. But if water is reacting with something that's a stronger base than it can be, then water will act as the base. So it just depends on what it's reacting with. Okay? Water is actually is neutral, but it's because it ionizes, which we'll get to later. Okay? So it can act as an acid or a base. Just depends on what it's reacting with.
No. Because you ought to add acid to water.
Okay, so if you're adding strong acid to water, water would be acting as the base.
But what happens if it acts as an acid and then boom, you're just made stronger acid?
No, it can't do that. It won't do that.
How do you know?
Because I'm the teacher. All right, strength of your conjugates. Okay, if you have a strong acid, if you have a whoops, what's going on? I'm ready for this Monday to be done. If you have a strong acid, would you predict that it gives you a strong conjugate base or a weak conjugate base?
I predict weak.
You are correct.
Mine is so good.
So if you have a strong acid, it's going to give you a weak conjugate base. If you have a weak acid,
It's going to give you a strong.
it's going to give you a strong conjugate base. And we saw that when water acted as the acid, it gave us a hydroxide. A hydroxide is a strong conjugate base.
Right.
Okay? Same thing with bases. If you have a strong base, then you have a weak acid. And if you have a weak base, it gives you a strong conjugate. So they're opposite. Weak gives strong, strong gives weak. Okay? So if you have a left side activity that's going to ask you have two left activities. You have left side activities. The first one was naming some acids and bases for practice. And then the next one is naming your conjugates. Okay? And one of the questions on your left side activity is going to ask you to list two other things that are amphophthiric, meaning it can act as an acid or a base. So I want to give you an example of one. Okay? So a while ago, we said we had H2SO4,
Right.
and we had water, and on the other side it became HSO4 minus plus H3O plus.
Right.
Okay?
We did that.
So water is amphoteric because water can either give a hydrogen and become hydroxide, or water can take a hydrogen and become H3O plus. This would be another example of something that could be amphophthiric. And that's because it could accept a hydrogen and go back to being H2SO4. Or,
Just be SO4.
right. Or it could lose a hydrogen and become SO4 2 minus. This would be with water.
Can you leave that?
Okay? So that's another example of something that's amphophthiric. It can be an acid or a base depending on what it's reacting with because it has to have the ability. So when you're asking yourself if something has that ability, you need to look at it and say, can it accept and donate? Okay, can it accept and donate? Okay, and there's not that many substances that can, but there are a few. Okay? Now, NH3 is not one of them. Because NH3, the only thing NH3 can do is accept and become NH4 plus. It can't go to, can't lose anything.
Got it.
Okay? All right. That takes us to our, that's on your homework. That's your left side. Takes us to the last definition, which is called Lewis. There you go. Lewis. And that is the Lewis acid-base definition, and it is the loosest definition, and I did that on purpose. Lewis is the loosest. Good L's and L's. And that means there are going to be more things that could be considered an acid and base under this definition. And really all we do with that is you got to know the definition. Most what we're going to do with this has to do with Bronsted-Lowry. The Lewis acid accepts electron pairs in covalent bonds. And the Lewis base donates electron pairs. So this time we're not talking about hydrogen, we're talking about the electron pairs. So what happens is you see this little lone pair on here on NH3. It's going to donate that electron pair, and then we form this bond.
Should we draw that?
You should, because this is the classic definition. These are the classic examples of Lewis acids and bases, and most likely this is the one you'd be asked about, because it's like the standard one that they use.
And lone pair.
Don't move it.
Don't move it. Wait, are you using all
We are supposed to draw them.
Yeah, go ahead and draw that example. Because that's like the classic Lewis acid base definition. Even in AP Chem, we don't discuss Lewis acids very extensively. It's really more organic or inorganic that you do, because it has to do with covalent bonds.
So this Parker, did you hit chess this morning?
Say what?
Did you hit chess this morning?
I'll discuss that after we're almost done.
Usually Monday's chess day.
I do it a little differently.
Oh, okay. Ooh. We're mixing it up on us.
Okay, are we still writing or are we done?
You go into 24-hour fitness at 5 o'clock on a Monday and see if there's an open bench press.
I don't ever do chess.
You know why? Because on Mondays there's never an open bench.
Okay, does everybody have this?
Why not Sunday?
The majority
And then at the bottom of your page is that all of those definitions summarized. So you should definitely, for the test, know what they're doing. Okay, that's why I gave you this little summary. And that, my dear baby chemists, is where we're stopping.
You don't have to really that again.